Okay, hello everyone. Today we will learn about probability, which is chapter 2 of our textbook. Okay, in chapter 2, uh, in chapter 2.2, there's probability and inference, and probability is a measure of one's belief in the occurrence of a future event. For example, if we are rolling a dice, there's 6 cases when you are rolling dice, from number 1 to 6. So these 6 events are possible events, and the relative frequency for the balanced dice, if dice is very fair, then the relative frequency would be 1 over 6 for each cases. So here it describes the relative frequency for each event, each 6 events. Uh, okay. And about the statistical inference, we make a hypothesis like the dice is balanced. And if we observe something like that, a gambler rolled dice 10 times and all 10 tosses result in ones. Um, okay, you rolled the dice 10 times and every time you observe one, probably it is it is highly impossible for the balanced dice, and gambler should be conclude that the dice must be wrong. It is not. It may be not balanced from your experiment. This kind of arguments are statistical inference, and when we are doing inference like this, we need probabilistic support. Um, and that's why the probability is necessary, and that's why you are learning probability in this section. So we need a theory of probability that will permit us to calculate the probability of observing specific outcomes, assuming that our hypothesized model is correct. Okay, so what it means? Assume our hypothesized model is correct, which is the dice is balanced, which means for each event the probability is 1 over 6, like this. For each event the probability is 1 over 6, and we observed 1 all 10 times, which is 1 over 6 to 10th. That would be rarely possible, which means that the dice may be highly skewed to the one. Maybe the shape must be um, maybe weird shaped. I don't know, but anyway, we do some inference using the probability. Okay, and the chapter 2.3, it's a review of set notation, and the reason we need the set theory is that when we are describing probability, um, we are putting probability on set, like we can describe probabilistic events as a set and subset and set, that kind of notations, like probably the whole set of events can be considered as total set, and the probability of total could be one, like that. So set theory can be highly related with probability. So that's why we are um, learning set, uh, learning about set in this section. And okay, let's get started. Capital letters A, B, dot dot dot. We use capital letter to denote set of points, and elements in the set A are small a1, small a2, and a3. And we write this way: if element a1, a2, a3 are element of set A, then we write it as this: A equals um, A1, A2, A3. And okay. And let S denote the set of all elements, that is universal set. So when we are writing as S, it means the whole set. Okay, and A is inside of B, which this symbol implies that A is subset of B. And also this sign is the null set, which means there's nothing in this set. So this one stands for null set. Okay, let's learn these set things by using Venn diagram. Okay, so A is subset of B. That implies that A is subset of B, and which means from the graph, the set A is inside of B. Here's an example. Let's say A1, A2, A3 are elements of set A, and A1, A2, A3, A4, and A5 are elements of set B. Since all the elements of A's are inside of the set B, A1, A2, A3, every element are also inside of set B, A1, A2, A3 here. So in this case, A is the subset of B, and from the graph, it can be represented as like this. The set A is here, and in the set A, elements are A1, A2, A3, and here A4 and A5 is outside of the set A, but A4 and A5 is still inside of set B, and here the S denotes the whole set. As we mentioned here, S denotes the set of all elements. So probably we have A6 and A7 here, and for the all cases or containing all elements, it's set S, whole set. And there's more set notations. Union of A and B. We use this kind of cup sign, A cup B. Yeah. It stands for union of A and B. For example, if A1, A2, A3 are elements of set A, and A2, A3, A4 are elements of set B, then what is the union of A and B? A and B must contain all the elements of set A and B. So A cup B contains A1, A2, A3, and A4. So this is A cup B, union of A and B. And if we have a union of A and B, then probably we also have intersection of A and B, which is this cap sign, A cap B. That intersection of A and B. So in here, the intersection of A and B, it implies that an element is included in both A and B. That's intersection of A and B. So from the example, let's say elements A1, A2, A3 are in set A, and elements A2, A3, and A4 are in set B. Which element contained on both A and B? Here, let's see. A1 is in A, but A1 is not in B. So A1 is not the intersection of A and B. A2. Um, A2 is here. Oh, that's probably I should correct this thing. The A2 and A3 are both inside of in A and inside of B. I will correct the slides after this recording, so don't worry about that. So the A cup B equals, yeah, A2 and A3. Maybe I can use pen here, A2. Sorry, I don't have the tablet yet, but I'm going to order tablet so that I can use pen here. So for now, I am preparing all the things inside of the slide, but when I have pen, probably I will replace these examples by my handwriting. But for now, I'm preparing all my slides with all my preparation inside of the slide. Okay, and the complement of A, we write it as A bar. So in the Venn diagram, the complement set of A is the outside of A. Um, yeah, and it looks like this. A is here, and A complement is here. This is just like S minus A. Okay, but we didn't learn about S minus A in the set notation, but it's like that. And for example, let's say element A1 to A4 are inside of the whole set S, and let's say elements A2 and A3 are inside of the set A, then A complement A bar equals to here in another textbook, the complements are sometimes C A complement and sometimes A uh, dash. These are some other textbook use this notation, but in our textbook, it uses a bar for the complement sign, and a um, complement of a is here a1 and a4 because a1 and a4 are outside of a. Okay. Uh, Yeah, and here's the last one. Mutually exclusive. If there's no intersecting items, if there's no element that A and B are containing together, then it means that um, set A and B are mutually exclusive. So, for example, if A1 and element A1 and A2 are member of set A, and if the elements A3 and A4 are elements of set B, then none of items A1 to A4, none of items are included together. So here, so A1 and A2 only included in set A, but not in B, and A3 and A4 they are only included in set B, but not in A. So in this case, we say it as the set A and set B are mutually exclusive. Okay, and yeah, and here's distributive laws and De Morgan's laws. Um, and there's rules like this. A cup and B cap C, which is A cap B and um, A cap C together, and then we cup uh, on those. So um, let's start from distributive laws first, and I will prove for this one by graph. So in the Venn diagram here, the A is here, the colored one, A, and B cap C is here. B intersection of B and C is here, and A cup this thing, A union this thing result in this. So the left hand side So left hand side result in this thing. And what about right side? What about right side? A union B. A union B is here, and A union C. A union C is here. And what is the intersection of A union B and A union C? Okay, what's the intersection? So from here, the intersection area is this area. So the result is this thing. So we can see that the left hand side result in this thing and right hand side result in this thing. So and they are same. So this is the proof of distributed law for this case. Um, the similar way you can check for the first two case as well. So you can do by yourself. And what about De Morgan's law? So the De Morgan's law is that if A cap B, intersection of A and B, and complement of intersection of A and B, that is equal to complement of A union complement of B, and also complement of A union B is equal to complement of A intersection with complement of B. We can check that using the Venn diagram as well. Here, let's check the left-hand side first. For the left-hand side, um, what would be the complement of A intersection of A and B. So intersection of A and B is here, and in the complement of intersection of A and B is this green area that we can see that, and here complement of A that's the area is here, and the complement of B, the area is outside of B, and then what would be the union of complement of A and complement of B? That's the same as this green area. So that's how we prove the first case. And for this thing, what would be the complement of A union B? Here, the white area is A union B, and the complement area is this green area. So, so this one is same as the green area. And what about here? Complement of A. Complement of A is here, and complement of B is also here. And what about their union? What? No, no, no. What about their intersection? Intersecting area is just outside of whole A and B. So we can check De Morgan's law from the Venn diagram like this. Okay. Yeah, this is end for section 2.3, a review of set notation. And for the homework problems are every odd questions. So 2.1, 2.3, 2.5, and 2.7, they are homework problems. So I will upload these homework on the e-class homework bulletin board, so you can submit your homework using the system. Yeah. Okay. Okay, so far we have learned about set, and now it's time to uh, propose about probabilities, time to assign probabilities on that set, on event. Okay, so in section 2.4, we're going to learn a probabilistic model for an experiment for the discrete case. And let's look at definition 1.1. An experiment is the process by which an observation is made. So experiment is the process. Just for example, tossing a die uh, could be an experiment. And when an experiment is performed, it can result in one or more outcomes, which are called event. Okay, so some event associated with a single toss of die. Here, a single toss of die is experiment in this case, and the events are result of the outcomes from the experiment. Okay, let's look at what are events. Set A can be event. A is observe an odd numbers. B, observe a number less than 5. C. Observe a 2 or a 3. E1. Observe a 1. These four sets are example of events, and actually um, we can specify them as sets. So for set A, odd numbers. Observe an odd number from a die, which are 1, 3, and 5. Yeah, we can specify them as set. Okay, and set B, observe a number less than 5, which the elements are 1, 2, 3, 4, and 5, and observe 2 or a 3. Then set C have element 2 and 3, and this one have only one element, 1. E1 have only one element. These are events. Okay, and in definition 2.2, it says about simple event. A simple event is an event that cannot be decomposed. Each simple event corresponds to one and only one sample point. The letter E with a subscript will be used to denote a simple event or the corresponding sample point. Okay, yeah, so simple event, it contains only one sample point. So from the example, from the previous example of single toss of die, here, these E1 to E6, they are simple event. Okay, so here E1 is observe a 1, E2 is observe a 2, and E6 is observe a 6. And also, the letter E with a subscript will be used to denote a simple event. The corresponding sample. So in this textbook, they use E with the subscript to represent a simple event. Okay, and here A, B, and C are called compound event, and E's are simple event by definition. Okay. And from definition 2.3, it says about sample space. The sample space associated with an experiment is the set containing of all possible sample points. So it's the whole set S in the set theory. In the previous chapter. A sample space will be denoted by S. So the sample space S contains every element. Like so, in the previous example, Venn diagram for the sample space associated with the die tossing experiment, the sample space S contains all simple event E1, E1, E2, E3, and to E6. So, and we can specify S as like this. Our sample space S equals to E1 to E6. Okay, this is sample space. And in definition 2.4, it defines a discrete sample space. And a discrete sample space is one that contains either a finite or uncountable number of distinct sample points. Okay, so in the previous example of tossing a die, um, it contains 6 simple points. The sample space S is equal to E1 to E6, and we can count it. There are finite number of simple events. So the S, this case, is discrete sample space. And let's say counting bacterium is our experiment. So we are counting how many bacteria there, and that's so if there's only zero, if there's no bacteria, that's E0. If there's one bacteria, that's E1, and so the events are correspond to the number of natural number. Natural number is the integers greater than 0. So yeah, so counting bacterium, it corresponds to integer that greater or equal to 0, and that's countable. There, even if it's infinite number, it's countably many events. Yeah, probably you know what this means if you learned about um, uh, if you learned some math classes. So natural number, it have countably many numbers, um, and what are um, then what about real number? If our sample space S contains like interval, real interval from 0 to 1, would it be discrete sample space? And actually it's no. The real number, that's uncountably many numbers inside of the real number. So that's not a discrete sample space. Okay, and the definition 2.5, an event in a discrete sample space S is a collection of sample points that is any subset of S. Okay, so an event in a discrete sample space S is a collection of sample points. Let's look at the example. So in the previous example of die tossing experiment, our sample space S have single points E1 to E6, and the any event like event A is a collection of sample points. Is collection of sample points E1, E3, E5. So A is odd numbers and set of odd numbers, and it can be represented as collection of sample points E1 to E5. And for B, it's also a collection of sample points E1, E2, E3, and E4. So event, and also for bacteria counting example, this can be also event. The number of bacteria is more than 200. That's also event, and the event B can be specified as E201, E202, and it goes on. Okay. And in the definition 2.6, it describes the axiom of the probability. So from this point, we are expressing the probability in mathematical way. Okay, so suppose S is a sample space associated with an experiment. To every event A in set in S, A is subset of S, we assign a number probability of A. called the probability of A. Oh, okay. So that the following axioms hold. So we define probability this way mathematically. So axiom 1, probability of A always greater or equal to 0. So the probability is always greater or equal to 0. And the axiom 2, the probability of S, probability of whole sample space is equal to 1. And for axiom 3, if event A1, A2, A3 from a sequence of pairwise mutually exclusive events in S, so A1 to A1, A2, A3, dot dot dot, they are exclusive events in the sample space F. That means that any AI and AJ, the intersection of those two events is the null event. Then probability of A1 union A2 union A3 union dot 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 can be expressed as sum of I equals 1 to infinity the probability of set AI. Yeah, that's three axioms to generalize probability in the set notation that we defined before. Okay, so these are some rules how we treat probability with set notations. Okay, and let's think about some examples. In the previous die tossing example, uh, the every event A in S, that's something like this. Every event, E1, E3, E5, each element of are event, and also A is event. So we assign probability that is always greater than 0. If we assume the um, the dice fair dice, then probably the every event would be equally likely. Every simple event E1, every simple event E1 to E6, probably they are equally likely. Then probably it would be reasonable to assign probability of EI as 1 over 6. So in this case, probability of event would be greater than 0, or yeah, greater or equal to 0. And the probability of S sample space, which contains everything E1 to E6, so probability of S equals to 1, and if A to something. So if we have pairwise mutually exclusive events, let's say A1 is odd number. A1 is odd number and A2 is even numbers. Then probability for odd number is 1 over 2. And probability for actually we can okay, and probability for even numbers also 1 over 2, and that can be the probability of A1 and A2, union of A1 and A2, that is S. So the probability of S equals to 1, and which is same as 1 over 2 plus 1 over 2. And yeah, that's example of axiom 3. Okay, let's look at example 2.1. A manufacturer has 5 seemingly identical computer terminals available for shipping. Unknown to her, 2 of the 5 are defective. A particular order calls for 2 of the terminals and is filled by randomly selecting 2 of the 5 that are available. Okay, so a manufacturer have 5 computer terminals. Here, manufacturer have 5 identical computer terminals, and among them, 2 are defectives. So 2 are defectives, D1 and D2. 2 are defectives and 3 normal things. And particular order calls for 2 terminals by random, and the question A is list the sample space for this experiment. Okay, so sample space for this experiment. What is sample space? Okay, sample space is an experiment a sample space with an experiment is that it's the set containing of all possible sample points. Then what are sample points in this experiment? So here, sample point, sample event. Each simple event corresponds to one and only one sample point. Actually, this means the only event that can happen. So in this example, um, let's let the 2 defective terminals be labeled as D1 and D2, and let's say 3 good terminals to be labeled as G1, G2, and G3. And the simple event is that would be only realization, in this case, sample event could be selecting all defectives, D1, D2. That can be our event. Um, so in here, experiment is selecting 2 uh, computer terminals. So selecting 2 computer terminals, that's our um, uh, event. uh, simple event. So E1 can be selecting D1, D2. Event 2 can be selecting D1, G1, and also D1, G2, D1, G3, and D2, G1. So all possible cases for selecting 2 terminals from 5, total 5 terminals. So these are all the events E1 to E10, and our sample space is listing all of them. So our sample space S is equal to E1, E2, and E10. Okay, and the problem B, let A denote the event that the order is filled with 2 non-defective terminals. List the sample points in A. So the event A is filled with 2 non-defectives. So in the event, what are events without defectives? Here, E8 to E10, they don't have defectives. So set A, event A is E8, E9, and E10. Okay, and the problem C, construct a Venn diagram for the experiment that illustrates event A. Okay, so Venn diagram contains all the simple points E1 to E10, and the event A, it contains E8, E9, and E10. So here as our sample space contains every event E1 to E10, and A contains E8, E9, and E10. Okay, and for the problem D, assign probabilities to the simple events in such a way that the information about the experiment is used and the axioms in definition 2.6 are met. Okay, so assign probabilities. We defined axioms in definition 2.6. We want to assign probabilities that those definition hold. And one idea would be imposing for every event we can impose equally likely probabilities, like for any event, for any realization, they are equally likely, so we assign probability 1 over 10 for each event. Okay, that would be reasonable assignment of probabilities. And what's next? What's next is find the probability. And before problem E, we can also check the definition of 2.6 with our assigned probability. So in the definition 2.6, the axiom one is any event in the set is the probability is greater or equal to 0. And if with this assignment, you can check that. And for the axiom 2, the probability of whole space, probability of S or sample space equal to 1. And actually, we have 10 events, E1 to E10. There are 10 number of events, and all probabilities of each simple events are 1 over 10. So if you sum up every event, then it results in 1. So the axiom 2 hold. And for the axiom 3, you can try manipulate all the events, and you can simply check that axiom 3 we're going to hold with this assignment. Okay, and for problem E, find the probability of event A. So in set A, A is a union of E8, E9, and E10. By axiom 3, the probability of A equals to probability of E8 and probability of E9 and probability of E10. And each probability for these are 1 over 10, so the result is 3 over 10. Okay, and that's all for chapter 2.4. And homework for chapter 2.4 is these. So, okay, thank you. Actually, there's one more thing. As you may have noticed, the homework problems are every odd numbers for now. And probably I'm planning to make every odd number as homeworks. And in the future, maybe if it is too many, probably I will reduce some numbers. But for now, you can think that every odd numbers are homework problems. Okay, and so far we have learned set theories, and then we learned about probabilities, how to assign probability on those sets. And okay, thank you. See you next week.